In this video, we'll decide if the series whose terms are 1 over n times the log of n squared converges or diverges. I've decided to start the series at n equal to 2 because at n equal to 1 the logarithm is 0 and I would be dividing by 0, and that avoids that issue. One approach is to try to use the integral test. So I'm going to let f of x be the function that generates the terms of my series, 1 over x times log of x squared. If you were to plot that, starting at x equal to 1, where there's a vertical asymptote, you would see a continuous function. In particular, it's positive on 2 to infinity. It's a continuous function on 2 to infinity. And also it's decreasing on that interval as well. Therefore, the integral test can be applied. Those are the conditions required of your function before you actually apply the integral test. And it makes sense here now to look at the integral of 2 to infinity of my function. If it converges or diverges, that will tell me what happens to the series as well. This series, or this integral, is best handled by dealing with a substitution. So I'm going to take u to be log of x. When I do that, the derivative is 1 over x. And we'll be able to carry out that substitution. I'm really just integrating 1 over u squared, and the 1 over x gets swallowed up into the differential du. This is an improper integral starting at 2 to infinity. When x is 2, I will start now in the new integral at log of 2, and as x gets large, the logarithm goes to infinity as well. So I'm going to be now integrating from log of 2 to infinity. As an improper integral, it's a limit. I'm going to let b go to infinity. And I take the definite integral from log of 2 to b of u to the minus 2, just rewriting the integrand as a power now. So it's a limit. We'll find an antiderivative and then evaluate between b and log of 2. Just simplifying the expression, u to the minus 1 over negative 1 is negative 1 over u. And then we evaluate at the two values, minus 1 over b and minus 1 over log of 2 now. And as b gets large, what's important is in this first term, this term here will in fact go to 0. And so what's left over is this constant term here, and therefore my improper integral in fact converges to some value. That value that it converges to is not relevant here. All that matters is it does converge. By the integral test, my series that I'm interested in that is generated, whose terms are generated by this function, also must converge, and we've answered our question now.